Welcome back again. So, on the last video, we finished solving this operation between these three matrices, and you saw that when we do by hand, we can commit mistakes on the middle of the way, on the middle of the operation. And actually, it was a good thing because um, it was the perfect opportunity to start to use the octave environment. So we use the octave environment um, to solve these matrices, and we can consider large matrices because they are of order 4. They are matrices 4 by 4, and you saw how can this be. It take a lot of time from us, and as I said, we can commit mistakes on the middle of the operation. Um, and we got this resultant matrix, which is a matrix of this transformation of cylindrical coordinates. So what characterizes a transformation of a cylindrical system? I write this description, which is from the book. Actually, this description is only on the third edition, um, which is the version in English that I'm reading. So what describes a cylindrical system with cylindrical coordinates is that we will got two linear motions and one rotation. Actually, let me reformulate this. What describes a transformation on the cylindrical coordinate on the cylindrical system is that we will get two linear motions, which are translations, and one rotation. So with this description, this is an example with this description, a sequence of a translation of R along the x-axis, and this R is from ratio, and a rotation of alpha about the z-axis, and a translation of L along the z-axis. So when we are capable of interpreting the text, which is the description of a task that a robot can be doing, so when we are able to interpret this text description, we can draw what is going on, and we also can write the transformation equation, which is within this description. Okay, the transformation equation is describing the motion that this robot is doing. Actually, also, that is not a robot itself, is just a, we can call a vector p, but is a analogy to a robot arm. Okay, and I said that we can have this tiny mechanism which has the ability to stretch itself, and after this is doing this rotation, and after this rotation it does another transformation, but now again of a translation, and it said that is about the z-axis. But as you can see, and we also can confirm this just by looking the coordinates, this transformation, the position of this robot is not above the z-axis, is outside of the, is not above the z-axis, is outside, as you can see. It's just the, we can only look on the end factor, and let's say that is the end factor, which is the point of the vector, and as I said, is outside of these planes. So that is zy plane is outside of this plane, and when is above, we will got coordinates this way. This type of coordinates is very intuitive, and I draw right here this point. The end effector is outside of any of these planes, and so we solve this operation. Each matrix is representing the coordinates of each transformation, and after this operation, which is multiplication, we got the final position orientation, which results on the localization of the end effector, and we got this matrix. And this video, this last video, was the second part, and actually I wanna release this third part, and we will do something very nice, which is how we can, after this series of transformations, how we can get to the origin where the end effector actually where before these transformations, where it was this mechanism, or mathematically speaking, the position and the orientation of this, now let's say, point right here. We are not already working with differentials, but you can consider this as a differential because we are talking in terms of point in vectors. And let me introduce this to you, explain why we will do on this video. The three first columns represent the orientation of the reference frame after this series of transformations. So these three first columns, and now I'm not so sure if this description, three first columns, is said that is this three first, is this the right order, 1, 2, 3, or if the order is 1, 2, 3. So on this video, for me, it's gonna be very nice because I want to work with you. Since this matrix, we will project all these elements, and is an opportunity to you to learn how to do this, and I will do step by step, and also rework some concepts. So let's see. So the three first columns represent the orientation of the reference frame after this series of transformations. So let's interpret this. After the series of transformations, so if it's saying that is after the transformations, we can already discard that is referring to this point, because it's after the transformations. So these three first columns, these elements of this matrix is representing this point, the position and orientation of this point. Okay, this point right here. Okay, and but on this first moment, we only are interested on the position of the origin of the reference frame, which is the last column. So again, I don't know if it's referring to this column or this column, because it does not let clear what are the order, okay? It could be this order, 1, 2, 3, or it could be this order. So we will find this. I will copy this matrix, and we will try to represent each of these elements on the cylindrical coordinate system. So let's draw. So is the z-axis, the x-axis, and the y-axis. And let me spin a little bit. Okay. Okay, now let's draw the vector, which we can do an analogy to a robot arm. Okay, and let's call of B. And also you have to get the sense of views right here. Let's say this is an eye, and we are looking to the ZX plane. So this plane right here is the ZX plane. And notice that we have to have the sense of the views, so this you get with the experience. Okay. Also let's draw just the simple XY plane, and remember how we decompose the vector on its components. So that is the y-axis, and that is the x-axis. And again, we have a vector. This is the origin of the vector. And we have this vector on the y-x plane. So the vector is on the xy plane. But right here, as you see, we will decompose in components this and the vector, which are doing an analogy to a robot arm. This orientation and position, which is resumed on the localization of this point, is outside of these planes. Actually, is more on the let me repeat. Actually, it's above of the xy plane, as I already draw right here. So right here is something very much like this. Okay, is outside of the xy plane, but on the same time it is more on the xy plane than a combination with the z plane. But the z plane gives us the sense of depth, so we are adding another dimension. So with the z-axis, we turn this on a three-dimensional problem. We turn on a three-dimensional space. So right here we have only the xy axis, and this way you are forming this xy plane, the 2D plane. But when we add the z component, the z-axis, we are giving the we are adding one more dimension. So we got a right here is three-dimensional. Okay. So what I wanted to do is place each of these elements of this matrix on this XYZ plane, on this 3D plane. And now is another difficult that I'm having reading both English and Portuguese version, the second in the third edition. It not like it does not like clear and do not expose actually why the order if this is if this is the correct order or this, but with this example, after this example we will got the sense a better sense of this, what are the orientation and position. So now on this description is something that I just realized right now. So right here we got the orientation. So look how interesting this is in position. So we need three columns of this matrix to represent the orientation, and we just need one column to represent the position, which is the last column. So right here I'm saying that this is x, y, and z, and this is makes sense because let's take from this third line, which is the z component, we got this transformation with L dimension. So this L is from length, okay? This L is from length. So is a length that this vector is having, I don't know exactly, and is on the z direction, is on the z dimension. So okay, so this first guess, let's say, is correct. So this line is for z, this is for y, and this is for, sorry, that is for x, y, and z lines. So let's project the x and y lines. But right here is the view, which is the scalar factor that we add, so we are able to do operations with this matrix. Also, I think I will have to add a negative axis. So let me add this negative axis for y and for z. Okay, let me drag this so we can have more space to work. Okay, so let's see this. The only problem right here is this sequence 1, 2, 3, or is 1, 2, 3. But let's see. Let's say that is the, and as we also have this R, and this R is on the same direction. Look, is on the same direction as the x, and at the same time above the x-axis. So R is above and on the same direction as the x-axis. So it's not so intuitive, but I will do with this order 1, 2, and 3, and let's see what we get. So is R, which is from ratio, and let's say is still this point, R cosine of alpha, but we will not write alpha right now because alpha, let's see, alpha is on the plane alpha is on the xy plane. Maybe we can place alpha, but how we can get a sense of angle right here this way? Maybe, probably. So this angle is alpha. So let's write R times cosine of alpha. So we got this first element, this first component. Now this component, and again R is from ratio. Right here is R, right here is R. R, R. Which is the maximum point that this mechanism that I'm saying that is a mechanism with the ability to stretch itself, it can reach. And right here we are decomposing this component. So it's R times sine of alpha. And L for the Z component, for the Z dimension. But right here we only are working with the X and Y dimensions. And we don't have Z. We will have Z if we add the Z dimension. Now right here, and let's say that we are working this description. The three first columns represent the orientation of the reference frame after this series of transformations. So that is the descriptions of the transformations, okay? And right here, remember that, I don't know if I said, is very intuitive if you are considering that is the coordinates. Let me see, let me write each of these coordinates, the origin of each of each x, the origin of each, let's say, vector. If you already have uh, revised vectors, let's say there's 0, 0, 1, oh sorry, 1, 0, 0, and for the x-axis is 0, 1, 0, and for the z-axis is 0, 0, 1, which is the origin of each axis. So those are points. Okay, so if let's say we are representing this, let's say that is a vector. Let's say we are representing this x vector, but is a axis. We are only doing a analogy with a vector. So we don't have the y vector, the y axis. So this is x, y, z. Okay, and let's say is a unity vector which it has this, and let's say a length of 1, a scalar value. I don't know, sorry if I'm saying something wrong. I'm just trying to remember some linear algebra theory. And that is the same for the other axes or vectors doing this analogy. Okay. So 0, 0, 1, and this line, this element is for z, and I say that z, it got this element L as its length. So I don't know exactly why these coordinates, but as I'm explaining right now, something like this, I don't know exactly. And now this column, this third column, now I will suppose that we are decomposing, but as sign is negative. So what I will do is I will mirror this, like is something that we need to do in order to decompose and got this element. So I'm doing like the reverse process. So I'm mirroring it, and this way we got, let me see, this is the, right here also is R, and again R from ratio, which is the maximum ratio that this vector are reaching R. And when we are decomposing, we got this minus sine of theta, and for the cosine, but cosine is positive. So see, with this video, that is the purpose of this video, is an opportunity to you to learn how to do a analysis. If you don't know how to write, how to draw graphicals, and doesn't have a sense of how to decompose a vector. So this video is more for this type of analysis instead of getting a result. Right here we are doing just analysis, but I hope I can show to you something that we can do in order to get is a reverse process. So after these transformations, which are described right here, if we multiply by a rotation matrix with the value of alpha negative and working on the referential uh, frame NOA using as reference, we can reverse the process and got the initial origin, which we is resumed on the localization of the, let's say, point or vector, but this vector, it comes already for us with this uh, orientation position. So let's see. So cosine is positive, and what do we get right here? Now let's say we are adding the z-axis, but you will don't see the z-axis right now because it's like outside of the screen. Let's say the z-axis is pointing outside of the screen. Is this cycle? But where is the end effector? Where is the end of the point of the vector? Because now we have this sense of position and this sense of position. And actually, what I'm looking right now, what is passing to my mind is as we are adding this z-axis and now having a three-dimensional space, we can have a better sense, a more accuracy system, so we can start to think in terms of coordinates, and that is pure sine alpha, pure cosine alpha, and right here we are working with the length of the the ratio of the mechanism, the ratio of this vector, which is the maximum point that this vector, that this mechanism can reach. So this way we have a better sense of a better accuracy system. And for now, that is the only analysis that I can do. And now let's try to add these elements of this matrix with the z-axis added to the system. So now we got a three-dimensional system. Right here we are doing a analysis on a 2D system, and this is our limiting limiting us to be able to place all these elements, all these terms on the plane where this vector is on it. So as we got the sense of the XY system, so you can see, and again you have to have the sense of view. We are looking right here, and we are seeing the x, y plane. Okay. And also take in consideration that the guess that we said the order is 1, 2, 3 is correct. So now let's decompose this vector on its components. So for x, you saw that we get or cosine of alpha. So right here. And before establish a point, I will just cross the axis. We know where the point is right here. And just by crossing the composition of this term or cosine of alpha, you know right here that is or cosine of alpha. So let's say right here is alpha, and if this is a 90-degree, I don't know if we have some relation, and we can also say that this is alpha. In some point that there has to be alpha. And right here is R, which is the maximum point that is this vector, this robot arm doing this analogy can reach. Cosine of R, cosine of alpha. And for Y, and Y is right here. And just by having this experience, and you got this in real time, look at this. I crossed this way, but this way is pointing in which direction? Is on the same direction as the z direction. If I wanted to decompose on the same direction as x and y, I have to do on the same direction as they are. So let's see. But now I have to be wisely, because how can I know where is going to be the end of the crossing line that I'm using as a reference in order to decompose these components? Well, now as we are at the z dimension, let's use it. So that is the end vector, that is the end of the vector. And now let me draw a line parallel to the x-axis. Okay, is parallel, and also a line parallel to the y-axis. Okay, now let's just cross the line, a dashed line, and trying to as we are using this third dimension z, and we know that this vector reached a maximum point with this ratio value, this R from ratio, it can be a real value. And now let's take this. You see that we have to decompose this component on the same direction as the axis. So this point and this point is R sine of alpha. But now that's nice. Let's use this x-axis, and now again doing a line parallel to this axis, and it says that we are doing a transformation of rotation. Okay, so let's see. We are doing a transformation of rotation right here. But this point can cross the R value. So we are, with this dashed line, we are crossing all this plane, but we can have the origin of this line right here, so it can be right here. Do you agree with me? It can be right here. It can be right here. It can be at any point, but of course is right here above this dashed line. So I will erase this. And where is it? It's alpha. It's alpha. So is a rotation about alpha, and it cannot be on this region right here, because on these regions that I'm passing this dashed line, it's outside of the R value. So again, I will use the resource that we got. So it's just draw a parallel line, and I will draw a parallel line to the axis. Right here is R2. So sorry, I said that right here is outside of the point, but actually at this point. But we can have a sense as we use first the point of the end of the point of the vector as reference. But so that's nice, because look at this. That means the end of the vector P can be neither on the maximum point, on the maximum value that the R value is, or something within it. Because let's say We can put this vector right here, but never it cannot be a point that is outside of this region. Okay. But this is R, or let's say R. We are talking in terms of ratio. Now we have to think in terms of the trigonometric circle. So how we can plot this, something like this. And right here is R, okay. So it's something like this. So it can be on this region, but it's right here. Let me change the color with yellow. It's right here, right here, right here, right here. Where is it, the origin of this reference after the transformations? So after the transformation, we got this point, but this is the origin of the transformation. Let me see. At this moment, we are only interested on the position of the origin of the reference frame. Origin. That is the key. Origin. Right here, right here, right here, right here, where? Well, now we will be smart. R is generic. So if we have to work with a value, will be the maximum value of R. So actually what we will do is change this vector. It's something like that. Is that type of problem that you get from physics book, that you have to work with the generic values. We are not assuming a value like 1, 0, 2, 3. We are assuming that is R. We are not replacing those variables with values. We have to work with they as a generic values. So the point is this maximum point something like this. And again, I'm doing this analysis in real time with you. Is at the moment that I'm studying the subject, and I don't know if you will find another videos this way, but if you find it, come here and say it on the comments, and I will also watch this video and guide myself. I'm using the book, and so far we are doing well. So let's keep going. Okay, so let's say we indices is the length. L is for length. Right here is the length. Okay, so let's say we we are able to place all these elements on this graphical, which was this column. And what about this column? What are these components? What are these elements? As we are working with the z dimension right now, and is it what I said to you? Um, I don't know if it makes sense for you. That's what x, y, and z. So this column is this origin. This is for x. Okay, and this point is this column, this first column, if our guess is right. R cosine of alpha, R sine of alpha, and L. And this third column, minus sine of alpha, cosine of alpha. What is it, this element, these components? Let's see. Again, I'm doing in real time, so you're studying with me. And it works when I'm doing this. As we already work the sense of 2D, if we are saying there is a now again you have to get the sense of depth, the sense of views, dimension. Let me see if we can rotate this. Okay, so let's use this. Let me rotate. Oh, now it looks nice. Let me make bigger. Okay. So right here we said that is cosine of alpha. And right here R sine of alpha. So I'm guessing. I'm not sure if that's right. I will say that right here is minus. Let me see, because it's minus sine of alpha and cosine of alpha. Forget about this. I don't know if it's right, but thinking about it, the orientation is like the direction. Let's say it's pointing to here, to here, to here, to here, and the orientation we can define using cosine, in this case alpha, and sine of alpha. So let's say this column, the third column, is for orientation. So I will let this because I'm not so sure, but again, I'm studying this. So this third column, cosine of alpha, minus sine of alpha, minus sine of alpha, cosine of alpha in 0 is the orientation, which is different from position, and the localization is both together, is a composition of those two parameters, position and orientation. With those we can get the localization. Those are terms that we have to use to when if you wanted to work with robotics. And as we got more experience, we will got a better understand. Okay, so now I will do what I'm saying, since the end, sorry, since the beginning of this video, which is apply a technique which allows us to, it's like do the reverse process when, and we got the initial, the origin of the point, the vector. So let me write what the book says. We can restore um, the original orientation of the reference frame turning or spinning, I don't know exactly, sorry, what these terms are correct, actually is rotating, and it make more sense. We can restore the original rotation of the reference frame by rotating. The NOA reference system or frame, which is the end of the vector and the point of the vector, the end effector. So this point is the frame NOA, as I already have drawn right here. So if we apply a rotation on this frame, we can restore the origin of the orientation of this vector. And this rotation, it must be around the frame around the a-axis an angle of minus alpha, which is equivalent supposed to multiply the cylindrical coordinate matrix. This one that we got. This is the equivalent cylindrical coordinate matrix. Okay. By a rotation matrix, by a rod matrix of rod about a axis with some negative alpha angle. And let me use a title to describe what this is doing. So with this, we are doing restoring the original orientation of the frame. And let's say that is the frame NOA, which is the frame of the end effector frame, the E frame. And this point can be at anywhere on this 3D plane, since it don't pass the ratio, which is the don't pass the maximum ratio. But now we will use the octave. So what we're going to do is multiply by, as the description, we will start the original rotation, multiplying the cylindrical coordinates, the result cylindrical coordinate matrix that we got. So let me copy all this. Okay. Let me make smaller. And we have to multiply by a rotation with these parameters. And another keyword right here is post multiply. And that means, and remember, and that is so important that I will write again the order of the transformations influence on the final result. And as we all the time reading descriptions, and as this example, let's see this example, right here the keyword is sequence. We are working with a sequence, so is a sequence, and that means it's not if it's describing a translation and after a rotation and after another translation, like we are doing right here, a translation, a rotation, and translation. If we, and you can see that that is a A, B, and C. So we are multiplying on even on the matrices, which is the most important part right here. Is we are following a formality, denotations. The correct way is to write the transformation equation with the order of the sequence. And if we change the order of the matrices, we will get a total different result. So that's something that we have to pay attention. So the order of the transformation influence on the final result. So we are post multiplying, and if you remember, that means multiply by the right or by the left. Let's see. Let me look for this. Right here, post multiply. Post multiply is multiplied by the left, or if I'm not wrong, because as I'm being guided by the book, hopefully I do not pass this wrong to you. Or let's just change. Let's say post multiply, we are multiplying by the right. Okay. And also let's check this. We have to interpret the text with taking care with all details. So we are rotating. So look at this. We are rotating the NOA frame around the x-axis. So let's take the a-axis, a-axis. So let's take the a-axis and apply a rotation. So that is the a-axis. This one. So we are applying a rotation around this axis. Okay. So let's write this matrix. And to write this matrix, we have to do another analysis. And it's very easy. As you can see, let me draw right here, very small. Because this reference frame, it's axes are pointing on a direction which is equally to this this axis x, y, and z. And the vector right here, and on the point on the end of the vector is r. And now I will do smaller. This I will make bigger. Okay, we are getting there. A N O A, and right here is X, Y, and Z. And if I placed right here, so let me take this vector of the way, and as you can see, the vector x is pointing on the same direction as the vector n. The vector a, the vector y, sorry, let me change the order. The vector, the x, the n-axis, sorry, the n-axis is pointing on the same direction as the x-axis. The a-axis is pointing on the same direction as y, and z on the same direction as a. So in order to write, let me copy this. Right here is a. Okay, let me copy and paste right below and use as reference right here. Okay, so in order to write this matrix, we have to consider that the vector A is pointing on the same direction. Sorry, the axis A is pointing on the same direction as the z-axis. So let me look for the characteristical rotation matrix of Z, and we find it. We find. Okay. Okay. And now, how we do a operation of multiplication of a matrix of order 4 by 4 between a of order 3 by 3. We are not able to do this operation, and that's a good opportunity to explain to you why you use the scalar factor W is for this type of situation. And if you watch the first videos of this series where I explain this, you'll find this concept. So right here, let me look for this right here. Why we add the scalar factor and work with matrix on its quadratic form, because this way it's more easy to calculate inverse of quadratic matrices than rectangular. And in order to multiply two matrices, their dimensions need to be equal, as you can see right here. So it's not the evaluation of the operation that we get with more easily, but it's also the benefits that is bring, which one of these is calculate its inverse. And I don't know, maybe there has to have more operations that is more easy to do with a matrix on its quadratic form. So right here we will add the scalar factor 0, 0, 0, 1, and the rest 0. Okay, and now what we will do is reuse the result that we got on the last video. We are still on this screen, and just now multiply by the result of this matrix. So let's say that D is equal A times B times C. So we got D. And now we need to pass this matrix. Let's recycle some line of code. Let me copy this, and let's see what we get. So it's cosine of theta minus sine of theta. Let's see. Actually, it's alpha. Again, I'm committing this mistake. Right here is alpha. If you saw the last videos in which I used theta, it's alpha. I only changed theta by alpha because, again, I copied the characteristic matrix and recycle its content. So it's cosine. Let me do better. Minus sine of alpha. Okay, so cosine of alpha minus sine of alpha. Right here is alpha, alpha. And 0, 0 now is a 4 by 4. Okay, and sine of alpha, cosine of alpha, sine of alpha. Cosine of alpha, 0, 0, and we have to add sims. Okay, and 0, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Zero, 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 1. Let's check. Right here is 1, right here is 0, and right here is 1, right here is 0. Now let's pass this as t. Right here, same column. Okay, now let's see. And we have to multiply d by t. And now let's check the result. Let me pass the result that we got on the book. And also we have to pay attention on the notation, which is very important. It's not a simple formality, it's the correct way. Is so much important than the correct result. And transformation of the cylindrical coordinate in rotation above the a-axis with a theta angle, and this is equal one zero 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 zero. Okay, 0 1 0 0 0 0 1 0 r cosine of alpha r sine of alpha L 1. And just by looking we can judge that is a translation transformation because we got its main diagonal filled out with ones. And now remember the name of this technique, the name of this procedure is restoring the original of the origin, just origin of the frame. And is this one. Actually is a, I got confused right now because we have this transformation of translation in this transformation. And again, if we are changing only if you are doing the transformations of translations, we will not change the orientation. We change the orientation when we do rotations. So as we can see on this draw right here, right here, this element, this mechanism is stretched to this point, and right here we are not changing the orientation. The orientation is the same. We are changing the position. It was on this position and it changed to this position. So you have to know the different and the definition of the terms orientation and position. And as we were doing this analysis, this column, and I said that it was the orientation. So now you know that when we do rotations, rotations change the rotation. So let me write this because it is very important. Rotations change the orientation. And after the rotation, which changes the rotation, we do another transformation of translation. And again, from here, the orientation, it doesn't change, just the position. It was on this position and we change to this position. Okay, but we wanted to know if the octave evaluate a satisfactory result. Of course, we can do this by hand, but I think the video already it got very long. So is this line for each column, and we might obtain this matrix. Now let's compare with the octave. And what we get right here, this 2 is square, so is minus sine square of alpha plus cosine square of alpha. What we can see right here is if we change the position right here, cosine square of alpha minus sine square of alpha, we got the trigonometrical identity, which is equal 1. But we are not getting 2 square something. Let me check and see if I pass something which is not right. Let me see. Is cosine of alpha minus sine of alpha, or okay, it's correct. And right here, cosine of alpha minus sine of alpha 0 0, sine of alpha, cosine of alpha 0 0, 0 0 1 0. Yeah, it's correct, but we are not getting a satisfactory result, and I don't know why. Let me check again. Let me take a screenshot and let's do this analysis. Let's use trigonometric identities. Right here, this one, cosine square of alpha minus sine square of alpha is equal 1. It's the trigonometric identity. Right here, what we can do, this video already got too long. Minus 2 sine alpha plus cosine of alpha, and I don't know how we can turn this into a 0, because another trigonometrical identity is cosine. No, actually, let's let's see, this term we are not getting a satisfactory result. This one also. Um, right here is correct, correct. Right here too, correct, correct. This whole column is correct. These ones are correct also. But for these ones, we are not getting a satisfactory result. Actually, let me see, this one is 1 because it's also the trigonometrical identity, this. And with the exception of this element and this element, the rest of the elements is correct. So that is something that I will investigate and try to find a solution, and if I got, I will pass to you. And for now, it's all. This video already got too long, but we could do a lot of things, and that's it. Thank you.